You see my presentation, is it? But do you see my presentation in the one moment in the presentation mode or the
It's in
same?
presentation mode, yeah, so that's
This
fine.
is this is the presentation mode now. Okay, good. Good. Okay. My name is Dhayalan Velauthapillai, and I'm a professor here at HUL Campus Bergen, and I lead one research group. It's an international research group which is called Advanced Nanomaterials for Clean Energy and Health Applications. We are nearly 50 researchers involved in this network. So it is led by HUL from here. So we'll just the next slide. So we have a lot of collaborators in Asia and US and UK. So we have institutions in Sri Lanka, India, South Korea, Singapore. Yeah. So so what are we working on? We are working with different technologies. Actually, we are working with advanced nanomaterials. So our as you all know, when you have nanomaterials, nanotechnology, of course, you could work with, you could play with materials so that you could change the properties of the materials such that the same material in micro size, it will perform differently than in the nano size. So you can just change the sizes of the nanomaterials such that you could get different type of properties of the material, the same material itself. So we are working with materials. We are working with new materials as well. We are trying to make new materials, synthesize new materials. So these materials are used in clean energy applications and health applications. As far as clean energy applications are concerned, we are working with new type of solar cells. We work with hydrogen. We work with energy storage, and we work with carbon capture. And in tissue engineering, of course, we collaborate with the tissue engineering group at UIB at the Faculty of Medicine. So what we do is we make scaffolds for stem cells. Uh, the biological research, of course, it is carried out by UIB, but we work both on designing the scaffolds, which could where you could place the stem cells. That is one thing, and we work with simulations as well. So as far as all these technologies are concerned, it is these are new materials such that we should, before synthesizing, we should work on simulation. We must know what type of materials we expect, what type of electrical and optical, mechanical performances these materials can provide. So in that sense, we have to model it, we have to simulate it. So we have a simulation group under our research group, which works on simulations. At the same time, we have a group which works on synthesis and fabrication of all these new technologies. And we are working on floating solar as well. So we have a unit in Sri Lanka. I can come back to that later on. As Sophia mentioned, Sophia is working with Resinrec. So we have two PhD scholars working with energy policies and management. One is at Resinrec here at HUL, and one is attached to University of Oslo. So we have a variety of research activities. So I will just mainly focus on solar energy here. As we all know, as far as solar energy is concerned, we get nearly 23,000 terawatts of power, solar power. So, but the normal use for a year is around, let us say, the power which we use, that is around 16 terawatts. The world consumption is 16 terawatts. So in that sense, the solar energy which we get in 1 hour is enough to cover the world consumption for a year. So we have enormous solar energy, but we have to use it correctly. That is the thing. So as we all know, if you have surely heard, if you want to cover the whole world consumption, energy consumption, you need to use just 4% of the total area of USA. So if you can install solar panels in that area, 4% of USA, that will cover the whole energy requirement. So we have so much of energy from the sun. Um, but as you all know that we are using 90% of the solar cells, or 90 to 95% of the solar cell technologies are based on silicon, material silicon. But this material, of course, it has band gap is one of the important factors as far as solar cells are concerned. But this material, which has an indirect band gap, silicon has an indirect band gap, so the absorption is not that good. So in that sense, the maximum fraction effectively used by silicon is only 468 watt per square meters. The irradiation is 1000 watts per square meters, but only maximum amount is 468 watt can be used by silicon, but not the whole energy can be used. In reality, it's just 250. Maximum is 250 watts can be used by per square meters can be used by silicon based solar cells. So it is maximum will be just 24-25%. That's it. So you cannot go beyond that. People have been working with these type of technologies for many years, but you can't you reach beyond 25% now for the time being. So we have to use other technologies to capture the rest amount of the solar radiation. So that's what we are working on. Um, so I don't know whether you see that. So normally solar energy technologies are divided into three groups: first generation, second generation, and third generation. First generation is based on silicon based solar cells, which are on the rooftops. But you know that they are brittle, they are very heavy, they are very thick. So in order to find some flexible solutions, people have been working on second generation of solar cells. These are called thin films. So I don't know whether you all have heard about gallium telluride based solar cells, cadmium, copper zinc, tin sulfide, CZTAs, and this type of thin film solar cells. But the efficiency is lower than silicon based. But even these solar cells, of course, they consist of you know cadmium and these type of materials which are toxic. So people have been, for the past 20 years, people have been working on new type of solar cells. We call it the third generation solar cells. So we at HUL, we are focusing on emerging novel materials which can be used to produce the third generation of solar cells. They call it dye-sensitized, perovskites, and so forth. So just these are the ones. So we are working on. So we are working on dye-sensitized solar cells. We are working on something called perovskite solar cells, and we are working on solar windows. So what are these materials? What are these? Dye-sensitized solar cells, you just use dyes. You know, as we know in photosynthesis, um, the color, the chlorophyll, it absorbs the sunlight and it produces redox reaction such that you could get carbohydrate, glucose. So the fragments, the color pigments, color pigments can absorb the sunlight. So we use that principle here. So we use color pigments along with semiconductor materials such that it could, I will just show this here, it could absorb the sunlight and emit electrons. So if you see at this picture here, so it emits electrons, it goes through a semiconductor and it goes through a circuit, then you have it. Then you have electrolyte, then you have a complete solar cell. So what we are doing here is you can produce it in your own lab wherever you have color pigments and a semiconductor material, which is called titanium oxide. If you can use it, titanium oxide is used everywhere, in toothpaste, in food, and even in paints. So these are the materials which could be used. I'll just show one small demonstration here. I will just show this here. So this is made of color pigments, strawberry, for example, fruits, any color pigments. So you see here, so we have made two small panels, and you see, that's it. So it can be made, so it can be made in a lab. It is not a big issue. So what we think is in future, we can make these type of solar cell, very thin solar cells with very cheap materials. So you can use it wherever. That's what I normally say, that you can use it in your rucksack, in a bag, in your shirts, anywhere, And even you see here that you don't need sunlight. You need just diffuse light. So in a room, of course, you can have things which could produce current if you have these type of thin solar cells of disensitized type. So this is one type we are working on. And recently, people have been talking about perovskites. I don't know whether you have heard about it. Perovskite is a material which is used in solar cells nowadays. Instead of this dyes, you could use another material called perovskites. So if you use these perovskite materials, people have been getting efficiencies. Now already it has come up to 25.7%. So it can conquer uh, traditional silicon-based solar cells. So this is perovskites. It's a material which could be used instead of silicon. Silicon, of course, to produce silicon, you need a factory where you have to produce first, silicon material, polysilicon material. It has to be pure, 99.9999% pure silicon. So you have to heat the sand up to 2000 degrees, and you have to produce polysilicon. Then you have to produce ingots, and then you have to produce cells. You have to cut it, produce cells, then panels, and so forth. So you need a multi-billion factory to produce this. So, but these type of perovskite materials, you can just use it anywhere. You can produce it everywhere. So it is not a big deal. You need just to heat it up to 400 degrees to produce this material. So, so what we think is, in future, people are going to work with tandem solar cell. You will have a silicon solar cell. On top of it, you will have a layer which absorbs the sunlight, and the efficiency can be improved. So people have been working on it. We think that it could be increased up to 30% efficiency in just few years. So this is going to be the future perovskites. So I will just show one thing which we have been working on here. Sophia, maybe you are interested in this. Now people are talking about BI, building integrated solar cells and solar technologies. So this is one of these types. So we are working with solar windows. So I can just show you. We have a glass here, and I will just show you here what we have done. We have a material, we have a nano material which we have placed on this glass. You don't see that. It's very transparent. So you just apply this material, this Persian blue, and you just apply this material on top of it, and you do some synthesis there as well, and you place solar cells in the corners, and then you see you need sunlight, and of course you see it produces current. So these are solar windows which we have been making in our labs. So advantage of this is that you can have, windows which could produce current. It can be solar cells. So you can have it in different colors. So the problem with the solar cell technologies is that the amount of area you need. So if you can use the walls, if you can use the windows to produce current, so that would be the best thing. So this is one of the things we are working on. And this is the Norwegian floating This is a floating solar which we have installed in Sri Lanka. This is a pilot project, and we get results every day, the measurements every day from there. So this appeared in the Global PV magazine. So Global PV magazine is the magazine for, you know, all who are involved in PV technologies. So we are so happy, we are so proud that we appeared in this magazine, first page. So it's regarding the results which we have obtained from this floating PV. So hydrogen production methods, of course, you all know we have this high value. We are with high value, and we are working on green hydrogen production. So I don't want to go into detail on hydrogen here, but this is the high value center, and we are working. We are my research group. We are involved in one work package where we are trying to produce hydrogen in using novel methods. So we are working on producing hydrogen through three different types. One is photocatalytic. We call it photocatalytic, photoelectrochemical, and electrochemical. Just briefly explain it. First, electrocatalyst. What we do is, as you all know, if hydrogen is to be competitive, green hydrogen is to be competitive, then of course we have to reduce the prices. One way of doing it is to reduce the cost as far as the electrodes are concerned. Normally, the electrodes which are used for hydrogen production are made of platinum, iridium, ruthenium, and so forth. You see the prices. It's around $27,000 per kilogram platinum. Iridium, $55,000 per kilogram. So these cost a lot. So what we have been working on is to find some substitutes for these electrodes. So we have been working with different materials. We have been working with 25 to 40 materials, and we have shown that our materials, which we have produced, can be competitive and it can be used, but it is still in the lab scale. I will just show you a demonstration here, which we just presented last week. So here you see these are the materials which we have used, the electrode material, very cheap materials, new materials, and you will see that hydrogen will be produced now. You see the bubbles. In one electrode you produce hydrogen, and the other one you produce oxygen. So we have calculated the amount of hydrogen and oxygen we produce, so it can be competitive compared to platinum, you know, very expensive materials. But the thing is, it's still in the lab scale. We are just making it in small sizes, so we have to make it in big scale. So that is the challenge we face. Another thing we are working on is photocatalytic hydrogen production. So it is again the photosynthesis. As I told you, in dye-sensitized solar cells, when we were working on it, we found out that we could use it for hydrogen production as well, because the pigments, such as pigments, some materials, it could absorb the sunlight, and they can produce, the semiconductors can produce electrons and holes. The electrons and holes can be used into water, and then you produce hydrogen and oxygen. So that's what we are doing. So I can just show a figure, show demonstration here as well. So this is hydrogen produced just from a nanomaterial and solar energy. That's it, nothing else. You have water, you just put the material in, and sunlight. Then I think, oh, is it working? I don't know why the video is not working, but okay, it should work. But you see the bubbles here. So if you don't have sunlight, there won't be any bubbles. If you have sunlight, then you have bubbles. So we have a GC here. So we have been monitoring with GC the amount of hydrogen which we have produced. So it seems that our materials can produce a very good amount, and we have the best result for the time being. But it is still, again, it is still in the lab level. We're just producing hydrogen, oxygen, and we are not producing oxygen because we are using some scavenger materials such that we could just produce hydrogen. So that's what we need. Another small thing, we are working on supercapacitors energy storage as well. As you all know, supercapacitors can be used in, for example, in EVs, electrical vehicles, As you all know, the battery lifetime is a very important thing as far as cars, electrical vehicles are concerned. Normally, it's around, let us say, around 10,000 cycles. A battery will work for 10,000 cycles. So the thing is, when you accelerate, it needs a lot of power. And, so if you can provide something else instead of battery, you can use the supercapacitor. What happens is supercapacitor is a thing which could have much more power than the batteries. So these supercapacitors can be used when you accelerate the car. The thing is, you can you can charge it in just few minutes. A car battery, you need 10 hours to charge it, but a supercapacitor you can charge just in 5 minutes, 3 minutes. That's enough, and it can be used for 10 minutes. So that is the advantage of supercapacitor. But the thing is, you can't have much energy, so it is not a battery, but it can be used whenever you need, just like in a photography with a flash. When you need a flash, you use a capacitor. You store your energy in a capacitor. Just like that, you store your energy in a supercapacitor. Whenever you need it, immediately you can use it. So people are working on supercapacitors in China and in Switzerland. They have started using it in buses. So a bus which uses supercapacitor, it just moves for 5 minutes and then it stops at a terminal. Then it gets charged in just 30 seconds, then it goes for another 5 minutes. So these type of supercapacitors are very, very interesting in future. These electrical bicycles and these type of things. So we have been working with new type of materials for supercapacitors, and our materials I can just show you here. So these materials, some of these materials are new. It is not in the literature. So we have applied for patent. So it gives us good performances. So, but still in the lab level. So we'll see when we get the patent, maybe we could get some help from the industry. So another thing, we are working with CO2 adsorption. Here too, we are trying to use cheap materials. Here it is just rice husk. It's made of silicates. So silicates normally, if you make it in nanoscale, it could absorb CO2. So we have been using in small scale, and it seems that these silicates can absorb, the sodium silicates can absorb CO2 and NOx gases. So this can be used in cars, in catalyzers. So in catalyzers, normally they use platinum. It costs a lot. So again, here you have a material. So we are trying to work with in our lab here down in Machino Marine. We trying to use an engine to capture these silicates, the CO2 with these silicates and see how it works. But in lab scale, we get very good results. So these are the things we are working on. Uh, this is our group. So we have so here we have this energy lab. I think what we have to do is we need infrastructure facilities which has to be common for everybody, and we need partnerships with the industry. So I think BEL can do something on that. Yeah, I can stop here, Christine, if it's okay.